Today let's talk about Codeforces round 9A3 problem D. First part is the description. We are given an integer array n. That means there is a tree contains n nodes. We need to return the constructor of this tree. That means we need to return the parent's node for every node. There are three characters about this tree. First of all, after we remove the 0, for example, this is the tree. After the 0 is the root of this tree. After we remove the 0 and connected edge, the last thing will become path. Every subtree will become a path rather than a tree. Path means there is only one path to travel every node. So this means except 0, every node have only one, at most one child. That means for every node except node 0 only have one, at most one child. This is the meaning about the first limitation. In addition, for example, this node is not accepted. This node is not accepted. Secondly, the second character about this tree is for I is less or equal than g. Pi will be less than pg. That means if the index of this node is pi means the parent node of node I. This is the second limitation about these trees. Third thing will be the index. The node 1 have two connecting node. That means one of them will be 0. Another one always have another node. That means node 1 have definitely one child node. One have one child. This is the third limitation about these trees. So okay, for this problem we have some opportunities to query. For every query we need to output node A and B. That means this problem which will return two kinds of value, 1 or 0. 1 or 0. 1 means the path from A or B. Path A to B will contain 0. In contrast, it's not contain 0. So that means, for example, 1, 2, 3. Let's take this as an example. If we return, take an example, if for A equal 1, B equal 4, it will return 0 because this path will not contain 0. In contrast, if the A plus 1, B plus 6, it will return 5 because this path will contain 0. So it will return 1. In this problem, this is the description about query. So in this problem, we have at most 2 multiply n minus 6 times to query. After that, we need to return the constructor about these trees. That means we need to return every parent node for every node in these trees from 0 to n minus 1. This is the description about this problem. The next part, let's talk about solution. For this part, this is a funny problem, at least for me. We have this strategy. Actually, we need to we know the construction about the node. It will be this kinds of form. That means except node 0, every node have only one child. So the first thing we need to, there are two steps to know the form of the constructor about this tree. First is we need to know the width. That means, for example, this tree width is 3. That means no width. Second thing, or constructor. Width will be 3. For this tree, width will be 3. That means how many children nodes of node 0, node root. So we also know this will be node 1. For the second limitation, that means there is another details about the second limitation. Actually, if this is second, first there will be second 2, 1, 2, 3, 4. Actually, this must be the most suitable position for node 6. It will be 7. This will be 8. Actually, the next 9 should be the child node of 6. This will be suitable. But in this constructor of tree, this will be 9. This is actually the position of 9 because there is no node. That means if the 9 is the child node of 7, that means there will never child node for node 6, because let's assume there is another kind of node for the 6. For example, let's give it as 10. So if the 9 is less than 10, but their parents 7 is larger than 6, this cannot meet the requirements of second limitation. So we will know the best strategy to construct this tree will be we must add a node based on the depths of this tree. 1, 2, 3, 1, 2, 3. Actually, we forget the 4. 5, 6, 7, 8, 9, 10. This kinds of. But if we skip one of the strategy, we need to erase it, because it will never have children anymore. Yeah, this is the detail. This is detailed information about limitation of second. So let's come back to the step solution. One step and second step. First of all, actually we can check the 1 and 2. There are two kinds of solution, 1 and 0. If it's 1, that means this will be 2. It will be 0, that means this is 1, this will be 2. If it is this kind of situation, that means the 3 must be the child node of 2. And this is 3, this will be 4, we don't need to carry more. But if it is this situation, if it is 1 and 2 are both the children nodes of 0, we also can query 1, 3 or 1, 3. Yeah. Actually, we can query 1, 3. There are two kinds of situation, 1 or 0. If it is 1, that means 1, 2, 3, because 1 and 3 contain node 0. So if it is 0, it means 1, 2, and 1, 3. This kinds of 3. We will know the width 0, and in this situation, width will be 1. This will be 3. This will be 3. Actually, we don't need width. Let's take this as an example. For example, let's query 1, 4. We will get, let's assume it will return 0. That means 1, 2, 3, and 4. This is what we want to need. In next step, this will be width 4. In this solution, until this time, we will know what is the width of this tree. That means how many children knows of node 0 at this time. So this is the at this time we will know we finish the first step 1. Next step we need to check the last nodes 5 to the more nodes. There are two kinds of in this next part the first query will be 2 and 5 because the most possible value, the parent node of 5 will be 2. That means what we want to do is this will be 5. But there are two kinds of return. If it is 1, that means 2 is definitely not in node 2. That means 1, 2, 3, 4, maybe this can be 5 or this can be 5. That means that's why we will return 0. In another case of it will return 1, 2, 3, maybe 4, maybe 5. If it is return 0, that means between 2 and 5 there is no 0. That means 5 will be the child node of 2. So this is the way how if it is we can check the next step. We can check 3 and 5. We can check if 5 will be the child node of 3. If it is, we will know the position of 5. If it not, we can check the 4 and 5. In addition, if it returns 1, we will know there is no children. There is no children for node 2. This is the information we get in this step. Meanwhile, we also waste one-time query. This is the core point of this problem. We waste one time of query because after this query, we don't know the position of 5, and there are also uncertainty of position of 5. So this is kind of waste. This is how we check the position of the last nodes. This is how we solve this problem. In next part, let's talk about how many times we need to know the construction of this tree. First of all, for the width part, we need query key terms. That means key is the width. Key terms for k plus 2 nodes. Then, for example, let's take this as the example. So after width will be 3. That means there will be 3. For 3 times, we will know 0, 1, 2, 3, 4. There are 5 nodes. 5 nodes position. This is the first part. Second part is for every last nodes. That means n minus k minus 2. For the last node, that means last node. For last node, we at least need to query 1 time. So this is the times we need to query. Okay, this is also the times we need to query. The third part we need to query. That means times. Third part we need to query is the case of waste. How many times we will waste like this 2 and 5. That means after we query 2 and 5, if it return 1, that means we don't know the position of 5. So this kind of waste. And the largest possible waste will be k minus 1 because after we know there are only, we waste k minus 1 times. That means there are only, for example, 1 0 1 2 3 4 5. Okay, if the tree is this kind of situation, 5 is the child node of 4. That means there will never be child node for 2 and 3. So the last nodes will only be child node of 5. That means this is 6, 7, 8. So we need to add the child node one by one. There will be never child node for node 2 and 3. So we only need to waste k minus 1 times. This is kind of waste. Okay, this is all we need to query. Largest possible times we need to query. Actually, there are another detail. That means detail. If we really query k minus 1 times, we don't need query the last node for the second step. That means if it is this situation, we don't need to query for 6, 7, or 8, because there are only one possible path, one possible node which have child node. So if we really query k minus 1 times for situation 3, we don't need to query more for situation 2. So we can minus 1 for the whole answer, for the sum of these 3 situations. We cannot query the most largest possible times for situation 2 and 3 at the same time. It cannot equal the largest possible times at the same time. So we can minus 1 for the sum of the 3 kinds of situations. So the sum will be, first is k plus, second will be k minus n minus k minus 2 plus k minus 1 minus 1. This will be n plus k minus 4. We need to vs this. The requirement of this problem is 2 minus n, to multiply n minus 6. So we can erase the n, and this will be k plus 2 vs n. In this situation, we will know for the largest possible key, it can be this situation: 1, 2, 3, 4. K equal 5. That means except the width of the width, or how many children nodes of nodes 0, there at least 1 0 node, and there will be based on the requirement of the problem, nodes 1 have at least 2 connected node. So we will know k plus 2 is definitely less or equal than n. That means k plus 2 is definitely less than n. That we will know the sum we need to require is less than requirement. This is the improvement why this solution can be accepted, can meet the requirement before we know the construction of this tree. Okay, this is the solution part about this problem. I will paste my code below this video in the GitHub link. Last part is complexity. Actually, we don't. This is a interactive problem. So the time complexity is definitely less than 2n minus 6. It also be on, and the space complexity also will be on. Okay, this is all about our solution and the explanation about this problem. If you have any confusion, welcome to submit a comment below this video. Thanks for your watching.